Previously, we used the Addressing for Communication Devices software to establish the addressing for our BSSRT input and output information. In this video, we will manually create an implicit connection in our Productivity Suite software using the data addressing we generated with that software. We will also establish the connection between a P1 550 and the BSSRT, allowing the Productivity PLC to control the remote I/O using the data offsets. I will open Productivity Suite version 4.1.1.10. We will start a new project and select the P1 550 as our PLC. We can then click Go to Hardware Configuration. It creates a new project and opens the Hardware Configuration window. If we go to the EtherNet IP tab, on the right side is the EDS file library. There are some pre-installed options, but since we are setting up a manual connection without an EDS file, we will drag and drop Generic Client into the window. This will cause the software to open the Ethernet IP Client Properties pop-up window. We will use a structure and call it XEL-BSSRT. Our device name will be XEL-BSSRT as well, and our IP address is 192.168.27.120, since this is the IP address that we set for the BSSRT in our video on configuration. Now let's add a message. We click the green plus symbol and we will add an I/O message. Some of the fields are pre-populated with structure tag names, but we want to add a tag in the extended status field. This is technically optional, but most of the troubleshooting for Ethernet IP connections in Productivity will be greatly improved by having this detailed information available. We will call our tag BSSRT_extended status. For the message itself, we see there are 3 tabs. Since this is an I/O message, there is input data, output data, and config data. On the input tab, we need to decide if we need to include a run/idle header. We also need to select unicast or multicast, RPI time, assembly instance, and a data array to handle the information transfer. For this example, the Productivity will be the only scanner reading information from this bus coupler, so we will use unicast. Multicast would be used if we had several scanners using listen-only connections to the bus coupler in addition to our exclusive owner connection from the P1 550. RPI is determined by a balance of your I/O response needs and your available network throughput. If this number is larger, the lag between I/O changing and the information being seen by the scanner, in our case the PLC, will increase, potentially leading to poor system response. If it is smaller, the system response will be much faster, but the additional messages will increase the load on the network. If this gets too fast, the network can drop packets or even shut down altogether, depending on the networking hardware. For our RPI time, we will leave it at the default of 250 milliseconds. The assembly instance information for input and output on the BSSRT is listed in the help files. It is instance 161 for input data with no run idle header, and 162 for output data with a run idle header. Since the BSSRT doesn't use config data, it will allow a connection at instance 100, but the data size for the config data must be 0. That just leaves the data entry for the input information. The BSSRT uses a minimum of 16 bits for each input or output data section, so we can use a 16-bit word array for the data processing. To find our message data size, we go to our data addressing software tool. We set this up in the previous video on BSSRT data addressing, so please refer to it for further details. We see that for our setup, there will be 61 words of input data and 8 words of output data. Therefore, we will need a word array of 61 elements for the input. We will name our array BSSRT Input Array. Productivity will then prompt us to create this tag array before moving forward. We will leave it as a 1D array of 16-bit integer with 61 columns. This will create 61 word elements. Let's run the same setup on our output tab. This time we will keep the run idle header, as the help file tells us that our adapter expects that, and we will keep the 250 millisecond RPI and use the assembly instance of 162. We will name our array BSSRT Output Array, and we will create a 1D array of 16-bit elements and 8 columns. The BSSRT does not utilize configuration data, so we can uncheck the Enable Configuration Data box in the Productivity software. If you are working with a scanner software that requires a configuration assembly instance to be specified, use assembly instance 100 and be sure to specify a size of 0. Let's click OK, and it will prompt us to create all the structure tags for the Ethernet IP client properties. We will leave them all at the default and click OK again. We can now see our XEL-BSSRT at IP address 192.168.27.120. Let's close out of that window and choose a CPU for this project to connect to. The AutoScan in Productivity Suite shows us that our P1550 is at 192.168.27.50. We will select this, and when we accept it, the software asks us if we want to use our PC project or the project already in the PLC's memory. We have just created our project in the PC, so we will select No, Use PC Project. We can then transfer the project to the P1550, and now let's create a data view window for the Ethernet IP information tags we created earlier. The productivity software makes this very easy because we can go back into our hardware config, right-click on the BSSRT, and select Monitor in Data View. The software then asks if we want to create a new data view or use an existing one. We will create a new one. If we now double-click Data View on the left side of the screen, it will open our data view, and our second tab is the BSSRT information. None of the information is populated yet because we haven't initiated the connection. Let's enable the message by checking the box next to MSG1 Enable, and then send that edit to the CPU. We get the TCP connected return, the software populates the adapter name and vendor ID, and the connection online boolean also becomes true. Let's try and turn on the first output of our digital output card. If we go over to XG5000 and then to the I/O parameter screen, which is already open in our case, we see that the TN32A output card is in slot 2, which is the third slot, and that the first output point is variable %QX0.2.0. Let's add that to the monitor window so we can see when the module turns it on and off. We can also go into monitor mode, and we see that the output point is currently off. Let's pull up our data addressing tool again. We see that the TN32A will be at an output address offset of 2. Note that the first address offset is 0, so address offset 2 will be the third address. If we select the module, we see that it stores the output bits as 4 bytes of data, so our first output point will be bit 0. If we selected a more complex module, such as our analog module for instance, this information would detail which bits contained which key pieces of information, such as module or channel status. We go back to Productivity Suite and maximize our output array. Remember that it's the third address we're looking for, and the productivity software starts its array element number at 1, so we will actually use element 3, not element 2, to control the TN32A. Productivity Suite also has a cool feature to allow us to look at the individual bits within a word. We right-click on the element and select Show Bit of Word Details. It breaks out each bit as true or false. We can write a value of 1 to the word, which will correspond to the first bit being on. We send the edit to the PLC, and if we look back at XG5000, we see that the output point has changed to on. Let's go back to Productivity Suite and turn that bit back off by writing a 0 to the word. And back to XG5000, and the point is back off. Perfect. Reading information would be the same process, but with the input word arrays in Productivity. We are now able to control our remote I/O with our Productivity PLC by manually setting up an implicit Ethernet IP connection.